Hey guys, make sure you hang out in here. We're shifting to the energy center. I'll be in and out. So just stay online and I'll be right there. Hello, hello. I'm here, guys, in case you were waiting on me. Thank you. I'm heading downstairs. And a little rough start. I appreciate it. And this cart would be nice to have. Okay. I'm going to go ahead and just turn on our video here so you guys can see me. Oop. There we go. Excellent. All right. I apologize. We're down here at the Energy Center now, where we need to be. Let me do attendance and get us rolling. So just hang loose for a moment. And then we'll start talking about our lessons for the day, everything that we need to do. And then we want to talk about, let's see here. Anything else that we need to get wrapped up? So we've got Brian, Junior, and everybody here. So I'm going to go ahead and hit mute, and I'll get our attendance going. And I'll be with you in about a couple minutes. Here, what I want you guys to do, we're going to open one of these up so you can see it. So we notice, I'll get the rest of the class looking here. If we notice, we can see how much power that we're generating right now. Easier to see if I do this. There we go. 1.71, 1 point. So that we're almost 2,000, almost 4,000 watts between these two. As we've learned that we have a 6,000 watt inverter here, and we have 1.75, but that is, out of 6,000. Now we can go up to 5,000. So we're not quite at halfway. One other thing I like to point out is to check our sensor. So when we look at our sensor here, which I don't know if you can see if you can see that. Not very well, sort of. There we go. That should be good. So we're going to look at our, there we're at 468 watts. That's what you can't, I don't know if you can read that. It looks like it's ass backwards to me on my screen, but that should say 468. So 468 means 468 watts per square meter. That means we only have 50% of the sun available to us. So when we're looking outside, we're going to see it's probably a little cloudy out. Is it? Oh, yeah. A little cloudy. So we're going to see this number go up and down, and we can go over there and check. If we see this suddenly spike to like 2,000 or 3 or 4,000, then we can quickly come over there and look to see if that 468 went up.
So is this like how much is built up and currently?
That's how much watts. So that's how much actual power that the sun is making right now.
Wait, that's how much it's making right now, or how much is built up?
No, that's the sun. So the sun just went behind a cloud.
Oh, I see.
So we see it drop.
I see.
Now we can come back over here. So I'm going to swoop. Watch your eyes. Gotcha. Now we see our watts per square meter. What's it say now? That's 1,113. That's more than 1,000 watts per squared. That means something really odd. That means the sun is shining directly on our sensor out back. but not over here. So I expect any moment this is going to take off. There it goes. Starting to beat up, go up a little bit, but still.
Fluctuates,
Yeah. Whoop, it's trying to. Now we could go outside and see what's really going on, but let me get started first. So what we want to do is we're going to shut one of these down.
Some snow on the channels too.
Oh, really? Well, there could
I
be.
saw some fall when I pulled in.
Excellent. So we could go outside and do a little investigation here in a little bit. And for your guys' lesson today, what we're going to do is shut this down and we're going to open one of these up, but we're going to still have lights in here. So I think we want to shut down this one. So I'm going to do it right now. There she goes. We still have lights. Okay. Then that means we're going to also kill everything in here. And as you remember last week, that we did not have a dead panel in here, right? Because we have not shut it off outside. So we still have the solar coming in here. So what I want you guys to do is go ahead and open this side up only. Now that it's dead, take this off and this so you can see how it's wired. So when we're working over here, practicing your wiring, we're gonna try to mimic that. And that'll help you go a little faster, okay? And then we'll talk about it on the way. So I'm going to set this down right here. And you guys are going to watch them work on that for a second. I'm going to go grab my power cord and then we're going to get busy. All right, I'll be right back. When I do come back here, guys, here in a minute, I'll get our class all started. We'll go through all our information that we need to go through. And then we'll jump back on these guys as they're working on this stuff and we'll see what they're wiring up and we'll talk about it. Okay. So we turned everything off. I'll go get my bag. Be careful.
This is like not gonna shock this way.
No, you're okay. You're still. I think you're still. We're just taking it off.
Should we not mess with basically?
Just don't touch like where the screw meets the wire. Well, he'll explain it to us. He might turn this stuff off. He probably will. Okay. So. I mean, good. Pictures. Some ice cream on the way home.
Where's it?
So I mean, it's sandwich on the way home. There's some ice cream.
I'm not too sure I'm gonna do.
Culver's is always a solid choice. Okay, I'd say just put your screws up, or your bolts up there. Oh, man.
Alrighty. Got her open?
Yep, sir.
All right, excellent. So, first thing we want to do is you want to see what you have here and see what you have over there. Now, one last thing I want you to open up is I want you to pull this off and also pull this off so we can see the connections here too.
Okay.
Okay?
So like even this right here?
Yeah.
Yeah, and that silver thing's a little tricky. Doesn't necessarily.
Have you ever witnessed an arc flash happen already?
Nope.
All right, good.
Nah, it's just residential. So do you have to wear an arc flash suit when you go work in your electrical panel at home? No.
Okay.
Okay, so it's 24120. We'd be working with arc flash stuff if it was a lot higher voltage, more or less. You can. I got one. Do you want to wear it?
Oh no, I'm good. I was just curious, like I don't know, like what
That's
kind
a
of
good
level
question.
of risk these kind of things have.
It's the level of voltage and how much of it is exposed. And so there's a chart that you go off of. Very good. There's my keys. Okay. I'll open this up and turn that breaker off in there for sure, though. Okay. We totally don't have any power at all
Okay.
to our panel except for the solar coming in. Okay, the solar coming in is going to be PV disconnect. These wires here are going to have a voltage on them, so watch out for them. Okay,
So what parts should I not touch, basically?
so don't touch anything with your hands unless we go outside and turn off the solar power, which we don't need to do right now because you're not really working in this. You're looking at this.
Okay.
So what we want to do, I'm going to grab the rest of the class. All right. All right, here. So what we want to do is you're going to first, I'm going to get these guys going on their lesson. Then I'll come over and visit with you with the rest of everybody.
Gotcha.
And then what you guys want to do is, okay, look at this and copy it. What do you have over there that you understand and don't understand? And we'll start with those questions one at a time. So before you can even get that far, you're going to need to kind of get in your panel and look through stuff. So I can tell you these wires right here are most likely, they're on a breaker over there on that far wall, right over there. Okay. All right. I'm trying to, there we go. Look at my hand backwards. It's like a mirror. It's like, do I go this way or this way? So, well, that should be off. So you have one here and you have one here. So we're going to have to make sure if these are our voltage, we're going to check that later. But right now, you see they got wire nuts on them. Don't touch them. They should be dead, but we don't want to mess with these wires here. Okay? We don't want to mess with these wires here. They are dead, but you could go there and turn them on if you wanted to. Now, what we want to look at is building this like that over there. And then while we're talking about it, we'll talk about like some of the NEC code stuff. We're talking about like how do we wire between panels and disconnects, all that stuff in the charts that we've been talking about. So we're going to do that a little bit, but it's going to be, again, something we can't do in 2 hours, but we can get started on it and get as much out of it as can. Then on Monday and Wednesday, we're going to keep building these things. So the things that we can do as a group, because we're running out of time, is we have solar systems outside already built. We can go look at how you slap that stuff together, but we really look at that more in our 102 class. You know, we went outside and we wired that up in our 102. You remember that? You haven't got to do that yet. Okay, some of you did. And that's why we were testing series circuits and parallel circuits. We were wiring everything together and learning how that part of it would go. We haven't talked about that in this class so much because now we're looking at the code and how we would actually wire up all of this stuff correctly. So we would need a power source from the grid. This is the grid power source. Okay, well, let's go over here and let's identify that grid power source. Well, I happen to know that it's probably this one here. Okay, and so we have wires coming in. So where do these go? Well, they're running through these pipes here. This is communication cable right here. Okay, and then this pipe right here, that is coming from outside. Okay, and then we've got another. So we have wires that are coming from the grid all the way over here. Let's go over here in our panel, turn these lights on. From this panel, we have inverter 1 right here, inverter 1, inverter 2. Those are running, those are the grid feeds coming all the way over to those other panels that we've seen work. Okay, you have a grid feed is also, that's what makes these bimodal. I have got to get a new panel. That thing's driving me crazy. All right. So we look at this panel here, and we can see that we've got some new cables coming in. Okay, you've got an inverter 5. Inverter 5 is 27. Well, what is it? We got to verify that because we're in the middle of this. It's supposed to be 2729. That should be this 60 amp breaker right here. Okay, well, what is this 60 amp breaker? Do we have any other 60 amp breakers in here? Where are we getting our power from? So this stuff is what we were building before we got shut down, right? And this is where we're at. All right, so you guys are right back where we started. So what we want to look at is when we come over here, we want to look at the idea that we have these wires coming in and going over there. So a couple things you can do because you're building this is to try to trace them out, okay? Or we'll test them a little bit later is what we're going to do because that's just going to take a lot of time. I already know they're going into a breaker over there and then off, okay? You now understand that this is your grid power. So now we also need to bring in solar, and then we need to connect it to our batteries and everything else. We got a lot of stuff in here that we've got to wire up and finish. This right here is also mostly done, more done than that. We also can work on this. So some of the things that we can do as a class is we can finish wiring these up, these panels there and here, and hook any of the solar systems we have into them. We just have to hook them up. And then you can turn them on and see that they're working. But you can see how much work you have to do on those panels over there. You're building them. You're not just punching in little clips. So what I need you to do is continue to study this. As I start to talk to the rest of the students, you need to see, okay, if you open this side up, you still can see your labels. All right? So that tells you this is inverter 1. Well, over there, this breaker is most likely the grid. But you notice there's a jumper in between them. So that jumper allows you to not bring in multiple wires. So we're connecting multiple breakers here. So this is the grid coming in, okay? So you can see there's a wire on the backside here and a wire on the backside there. That is the grid. When we look over here, we can't see that, okay? But that's what we would see. We come over here, you don't have any jumpers. That's the first thing to know. You also don't have your power feed running into there. You got jumpers down here. So first things first, examine what you got here, examine what you got over there, and then start to make a list. I just literally find a piece of paper or put it on your phone or on your laptop, whatever you're most comfortable with. Yeah. start making a list of what we do have and don't have. Then we need to find what we do and don't have, because it's probably here. A lot of it's right here on this desk. And then we got to start putting it back together. Okay? And so you can see over there what looks different here versus over there. What you already have right here in front of you and on the table is really all you need to worry about right now. See what you have and don't have. Start working on that list. The first thing we need to do is get grid power into this. So we've got grid power here. That means we're going to have to bring grid power into this breaker. And then we're going to have to go from the breaker into this eventually. So when you're looking over here, that's what you're seeing. We're seeing right here on the bottom, okay, we're seeing we've got grid AC1. That's our actual grid power right here. So we see these 2 wires coming out right here, 2 wires, okay? And we can see, we can follow them with our eyes. They come right into this next box, right? Okay, now we got to ask ourselves, where do they go? Well, there are these soft cables. We can see that they're running up. And they're coming from the bottom side of this breaker, literally. Okay, I could be wrong, but that's what I think they are. So they're coming from the bottom side of this breaker and running all the way down, over, and into this inverter on grid AC1. That is the inverter. This is just a disconnect box. It's nothing anything more than a breaker box. This is where all the magic happens. We understand that. We also have a charge controller. We're not worried about that just yet. But what we can do is we can bring our grid power into our breaker. We got to come in the top side. So that means we need a jumper to go between the breakers, just like this, right? So we'll have the black and the red coming in there that you already have over there. Before we go cutting wires and landing them, we just need to make sure this is built. And then we need to understand that we're going to need to bring wires from the bottom sides of that breaker all the way down and over here. Now we can do that part without hooking the thing up to the grid. So you literally have these 2 breakers here. You got this and this. We're going to take 2 wires from the bottom side of this breaker, and we're going to bring them down and up into this grid AC. Same thing over here. You've got 1 breaker. You need more breakers, don't you? That's why we got to look at this. And Amazon has a store. We can order those today and get them here next week.
Oh, wow.
So we've got a list for Schneider. We looked at that online the other day. Remember, they had all these breakers that we needed.
That's right.
And we're missing a few. I know that. So we're going to make a list today of the stuff. We're going to build as much as we can, and then we're going to order everything else. And then next week, hopefully it'll be here. Yes.
What is this piece?
That's a grid bypass. So that is something that we have to have that allows us to switch between our grid and our critical load panel. Okay, we don't necessarily have a critical load panel with either one of these yet. We'd have to build it. Our critical load panel is that large panel over there. That is our sub panel.
One that's open?
Yeah, the one that's open that looks like a big panel. It's really not. It's a pretend main panel. The real one's in the closet. Okay, everything comes from the closet out. So we also have, if it's like something we can't do right now, we do have a second inverter here that we're not using that we could take some stuff from if we wanted to keep the ball moving today and get some things ordered. But before we do all that, this one's pretty good. It's all hooked up to these batteries and ready to go for a different system. But I think this is really where we got just wires hanging out. Let's do this. Let's build our stuff and make it work, right? And we already started on this one last week. So you understand this a little better.
Right.
Okay? So as I'm talking to the other students, trying to get them through anything else that we had for today, then I want you guys to just keep going back and forth and finding what you don't and what you do and don't have. So I do know that we're going to try to bring wires down from here all the way into here. Now, does that mean just hang wires right there and let them flop all over the place? You go over here and you can see how nice and clean they are, right? That means we're going to need to bring these wires and bundle them over to the side with wire. We got wire ties. We got all this stuff down in that little lab area. And if you can't find it, I can help you. So that tells you you're going to need some wire ties, wire straps, zip ties, right?
Mhm.
We're going to need, you should have a couple of these wires. Maybe there's a box, see them?
Yeah.
That we can get from here to here. So familiarize yourself and then work on getting that wire from here to here. That's your first task.
Gotcha.
Okay? And then start making a list of things that you know that you're missing.
Right.
Like I can't do what he does because he's got this and I don't have it. Well, you also got a lot of your stuff ripped out. Like this bar is just laying right there. There's several things missing from that too. So we need to get that stuff ordered. And that would be a big, big jump for us. Because by the end of next week, this thing will be on and running
Okay.
and making power. And you guys will have been able to have built it. And no, and I've got the proof on the video. All right. So I'm going to let those guys look at stuff for a minute here. Does any of you guys have any questions for me about what you're looking at or anything that you were looking at? I wouldn't expect you to, but if you do, just pipe in. Okay, so let's go ahead and take a look at our class shell. Let me finish attendance. Now that I got everybody here. Keep forgetting there's two of you here. That makes this list look smaller than normal. Okay, I think I got everybody. I don't see David and I don't see Caleb. I don't see Charlie. Jake, I think everybody that can make it is here. Cam had to cancel. David Smith. I don't have David Smith in here. Okay, he's usually here too. All right, I think that's it. Obviously, that's it. Hopefully, I have everybody. So we're going to take a quick look here at our syllabus. Looks like I'm recording still, so we're all good. So where are we at and what are we supposed to be doing? All right, so we are working on week 4, week 5 stuff. So we're still working on NEC PV wiring and we're trying to get our midterm exam done. So last class, oh, I shouldn't have jumped ahead yet. Sorry. Last class, we were right on the edge of getting that in, and that's been in there and it's ready if you just noticed it. I only added a couple of those questions at the end, but I'll take a look at that and see what's going on there. We will have for next week, we'll be jumping into this chapter 10. Like I said, there shouldn't be a whole lot of stuff to do there. We've been doing the projects already. So we're just going to be having an assignment and practice wiring. Then the next one we'll do a little more installing. So that's going to be more like the hardware. How would you do it? And we'll try to take a look at several examples when it comes to that. And then we'll have our final pretest, and then our last lesson is troubleshooting. So we should be doing just fine, okay? So that's where you're at, lesson 4, NEC PV wiring. And then as soon as I make this available, you'll just jump into that next lesson. Let's see what I got for you. All right. So the big thing, we have our week 5. I already had that available, so good. I'm gonna go ahead and take a look at that assignment 5, see any of you guys got a chance to work on it. Yeah, 3 of you have. So this is your lesson for the week. We do have week 5 available. All right, I just couldn't remember. But you're in week 5, and you've got your week 5 module here, okay? And then we've got our week 4, which some of you guys are still working on, I know. So you want to try to get that caught up here. And I think most of you guys have done that, so that's good. And then lastly, I want to take a look at the midterm, which I know we just got released. Just see how everything's looking on that. All right, so good high scores. 3 people. That's still a good sign for the rest of you. Okay, so that means that test is okay and making sense. All right, so get all your lessons done through modules 3, and then we've got that battery calculator, charge controller calculator that where it's going along with this test. Does anybody have any questions for me about the test or about the modules or anything before I get into the final part? I think we're looking at chapter 9 still. We want to go over grounding as a class, and then we'll check in on these guys here on what they're wiring. And then we're going to look at moving into the chapter 10 and get that a big chunk of that off of our lap. That's the goal of today's lesson. And then look at all this hands-on stuff. Now, one of the things you guys got to remember is the less of you guys that are able to come to class, the smaller the hands-on activities will be. When we used to run this class before the pandemic, right, we would have, say, 15 people in it like you have now. And then we would split it up like into 3 groups, like 3 teams of 5. And you literally would go out there and dismantle a solar system down to nothing and then rebuild it all the way. So sometimes we would do that where one group would dismantle one and then you'd have to switch, and then the other group would have to build the one that the other group dismantled. And so that seems to work really well because you guys get to see the whole thing from beginning to end, and it really helps you tie together what you need to do to make a system like this work. And if it doesn't have all those components, some are easier, some are harder as we're learning. The Schneiders are the hardest, but they're the most flexible and most powerful. The Xantrex, Schneiders, they're also in big industry. So that's why we want to focus on those. The smaller residential things like Solar Edge or microinverters, I'll be honest, anybody can build those once they learn how to do it. There's not much skill there. And that's just a fact. So that's like the difference of running MC cable, which is flexible conduit, versus bending conduit, like we do here, where we've got all our conduit back there all bent. That takes skill, the other does not. And there's a value to both. So in some situations, you may not need a great big expensive Xantrex inverter. You want something smaller. So we have that, and we'll look at that. But because we need to learn things that show our abilities and our skill sets beyond just what we've learned out of the book, we need to work on some of the harder things. So if you were to come to campus, say next week, I'm going to just put you in a group with one of these other people that are here, and then you're going to be able to try to build as much of this as you can. So we'll just start at one side or the other, depending on who's here. So if we have 4 people showing up, then that's going to allow us to mostly work on the inverters on the inside. If we have like 10 people showing up, then we might be able to go outside and inside. So right now we're going to focus on that. Okay? So I just wanted to help you guys understand what you may or may not be doing. And again, the way I explain it is, you can read about singing, but if you don't practice singing, you're not a singer. So you need to be able to practice working with this if you can. Again, I understand you got reservations about getting to campus. I'm not pushing anybody to come. I'm just inviting you. I'm inviting you and encouraging you. Okay? So now we're going to move on from that. Now that we know what we're supposed to be doing for our lessons for this week, we know that we had a midterm exam. You got lots to do, I know. Get all that done. That's a goal. Let's go ahead and jump into our PowerPoints. Does anybody have any other questions or concerns for me? We don't want the PowerPoints, do we? We want the book. Let's pull up our book. I know you guys have questions about those books. They're out there, and I know it's been a struggle for some of you, but hey, popped up right where we want it to be. So now we're on page 203 of the textbook is what it is. Excuse me. Okay. Again, any other questions? Any questions at all before I get going? Okay. So the first thing that we want to look at is, I don't know what, okay, is this chart. So this chart is important to understanding. It's called the grounding electrode conductor. So the grounding electrode conductor is the size of the electrode or the size of the service entrance conductor. So we have two things here. We have a ground rod, and then we also have a service entrance conductor. So the service entrance conductor is literally going to be the wire that comes in and allows us, the wire coming in, and it allows us to actually work on, allows us to size the green wire. That's what I'm trying to say. I apologize. So we need to find the green wire or the actual ground conductor. Okay, so what size is that? Is it going to be copper or is it going to be aluminum or a combo? We call it copper clad aluminum. So it's got copper on the outside, but if you cut into it, you see the middle of that wire is aluminum. So it's copper coated. Okay, so we have those two options. We also have copper. Then we have the size of the grounding electrode conductor right there. So I don't know if I have any of those. We're going to go on a little walk just so you guys can kind of see a little bit more what's going on at the Energy Center. So I'm going to stop sharing that. You can see we're going to go down to our lab. I really can't wait to get, I don't like carrying my computer like this. That's why I need that camera. So down here, you see we've got our lab and cleaned up for us. Thank you. Made it all nice and neat. Looks so much better. And then we have under here, we have our not easy. Well, I need a new door. I'll tell you what. All right, I don't like that. But we got some junk under here is what we got. But in here, I usually have a grounding electrode. I don't see one right off the bat. Well, what it's going to look like is a copper rod like this. This is what I mean when a grounding electrode, but it's solid copper. This is pipe, but it'd be solid, not necessarily solid copper. It's still going to have a little bit of aluminum in it, okay? But this right here is what we're talking about. And we bang this into the ground. Okay, so when we're talking about a grounding electrode, that's what it is. And we can go outside and look at them, but we have grounding electrodes here. When we do a system, we'll pull this stuff out of here, and then we'll go outside and we'll run it into the ground. Okay, so let's go on back to the lab. Now we understand that we're talking about a ground electrode, or the big long rod that we beat into the ground, right? And then we take our wire and we connect to it. That creates our ground connection. Okay, so when we're trying to pick our ground wire, we have to pick our copper wire, whatever the size is. You know, bigger is always better, but you want it to be, say, if we're running, you know, number 6 or number 2 wire, then we might want to run, say, a number 2 gauge, but see, it says number 2 or smaller. But it also shows over here that your grounding electrode is not going to get smaller than a number 8 or a number 6. So I'll tell you, we buy number 8 grounding electrodes, copper grounding electrodes, all day long. You go to Menards and find one. Let's talk about what that would be like. So one thing we can do is we can get into our Google Chrome. We can click on this. We can go shopping. Let's go to Menards. Right across the street, right? Okay, what is at Menards? We can type in grounding okay. So let's see what they got. They didn't like that answer. Hold on. Let's go back to our book. Grounding electrode conductor. Yeah, that's going to be an issue. So Menards is not going to have the right language. So we're going to type in grounding. Let's just go with this for now. So that is copper wire. Menards are failing me. So you're going to type into Google grounding electrode for sale number 8. Okay, there it is. So there's our grounding electrode number 8. So there's this company that's selling it. You see, it's about 15 bucks. Okay, it's 8 feet long, and it's 5/8 inch 6. That's supposed to be a number 8. Okay, so what we'd have to do is buy one of those. All right, let's try Menards to just see if Menards pops it up. I like to show places that you guys can go to. So like if you get inspired, you literally can just go on a trip over to Menards and go take a look at this. Physically touch it with your hand and go, okay, that's a grounding electrode. So we would buy that. You need a truck that has an 8-foot bed or a van because it's going to stick out the back. But you're going to take that back to your job site. And out there by your solar system, we're going to drive that into the ground because we're going to take our green wire and connect to that with what we call a football clamp. Okay, so I'm going to go back. I'm going to stop sharing there. We're going to go back down to our lab. Since we're talking about grounding, we're going to look at some of the grounding equipment that we have. All right. Stuff available for us that we can use. So we can use any of this. We're looking for clamps. I'm going to see what I can find. Well, this isn't a football clamp, but this is like a ground clamp. This is too small, I can tell you. But what we want to do is we're going to drive that electrode into the ground. Then we're going to put something like this around it and push our wire through it and tighten it down. And that's going to bond our grounding electrode to our green wire. Let's see what else we got here. like we just got more of these, which I need to get some more of, but I have an inventory of things for a reason. You guys need this, I can tell you right now. These are also those jumper bars that we were talking about. We got some of these jumper bars for those guys down there. I'm gonna help them with those. But it looks to me like we are out of grounding electrode clamps that are large enough, but you can still see that we have those available. Okay. Let's go on back. So we would need that. We would need a grounding electrode. We would need a grounding clamp. We would need the right don't see what you have and don't have. Look at that. We're up to 4,000. 4,000. Says 3.9. It's at full capacity. Let's go over there and look at our sun insulation. What the heck? It says 207. I need to move that sensor. So that's not jiving at all. It normally jives. But there's a reason why it's not making any sense. It's because we have too many clouds outside coming and going. So I've always wanted to move this sensor actually right on top. That's what we're going to do. I'm going to put it in a work order. We're going to move that sensor right on top of our solar system out there and our wind anemometer. Get rid of that tower.
Are you guys not having a snowstorm there?
That's what we need to do. Okay. So now that we have everything available for us, we are, let me go back to our book. Share screen. Share screen in our book. So we know we got to get a grounding electrode. If we're working with, say, number 6, wire. All right. What am I talking about? Well, when we're looking at this stuff over here, we can see, all right, you can see all these wires. Let me go ahead and stop share. Okay, now we can see all of these wires right in here. These are all like number 6. All the same size. I could be wrong, but we would have to, yes, it says right here, you can't read it, but I can. It says 6 AWG. 6 AWG is 6 gauge wire. We also notice that we have a green wire here. See, you got a lot of labels. I like to label things. We need to label things. Label things is good. So we have a green wire right here. This green wire represents the ground, equipment grounding conductor that we are talking about. So this green wire actually runs outside, all the way underground, out there by our solar system, and connects to a ground rod out there. So we can go out there and find that, but you would just see bare copper at that point, because once it gets out there and it's in the ground, we don't generally have insulation on it. It's just bare copper. But that is the grounding electrode. Now we know that we want number 6 because our conductors are number 6. So if we're running number 6 wire, we did all our wire calculations like we're supposed to, right? We've done all our wire calculations. And now that we have number 6 right there for our power conductors, like these wires here, all these wires here, every single one of those except these big fat ones. These big fat ones are 4-aught. These are 4-aught for our batteries. As we've learned, we want to run with 4-aught. These right here, these are all number 6. Okay? Number 6 can handle a certain ampacity. Okay? Let's find out what that ampacity is. How did we do that? Let me get back into this screen here. So now we know that we need a grounding electrode. We know that we need a ground wire. We know that we have this chart right here that is our code chart for helping us determine what size we need. We've already looked at a number 858 copper conductor. That's what we're going to do because we're dealing with 60 amp circuits. 60 amp? Who said 60 amp? Well, don't you remember? Didn't we want to use these right here? They say MPPT 6150, right? That means that these right here are our actual 60 amps. That's what we're limited to, 60 amps. Okay, we could put bigger stuff in here. We also have our list right here. I'm going to read this to you since I know it's hard to read. I'm going to try to get a little closer. Okay, so whoops, can't go any closer than that. All right, so this is the model for our charge controller. Our charge controller's maximum operating voltage, our VOC, is 140 volts DC. That tells you a lot. This thing's supposed to be a 150. We don't want to run it at 150. We want to run it at 140 or less. Okay, so when it's operating, then when we look at our actual VOC, all right, we're at 150 volts. You know, when we're talking about the VMP or the IMP or the maximum power, that's what it is when it's actually running. That's this right here. Let me go back and make sure the actual sizing of the system when we do our calculations is going to be based off of the open circuit voltage of 150. Then we also have our short circuit current, which is 60, which we verified. Our maximum battery charge current, 60. Our maximum charge voltage, 72 volts. That means this thing can do 6, 12, 24, 48, 72, 36, I believe, too. Oh, there we go. There they are. 12, 24, 36, 48, and 60. Not 72, but it'll do a 60-volt system. That's unconventional. So 48, 24 is what we're always going to shoot for. 48, because the voltage drop will be a lot less when we're dealing with that. Although, if you are paying attention and you don't have far to go, maybe a 12-24 system makes sense. Now, the range of the operating voltage, again, is going to move from 12 to 140. That means as the sun goes down, our voltage will drop. As the sun goes up, our voltage will increase. More or less, right? Same as our current. So that means this thing's functional between 12 and 140. Once we hit 140, this is not going to like it. It's going to want to shut down or fault out. So we know that that's some of the limitations. The maximum output fault current, 60. That's why our breakers are limited to 60. Okay, we also have auxiliary output terminals as we were in the last time, so we could run a 12-volt fan. And the minimum interrupt rating, 4,000 amps DC. Well, that's a surge from a battery, right? Why would it be so high? Because this is hooked into batteries. For overcurrent protection devices, certified for use with 90 degrees Celsius conductors. Remember how we talked about we need to determine whether we can run 60, 75, or 90? Well, this is a first indicator that we could put 90 on it. But that means every connection would have to be able to handle 90, and I doubt that. So we'd most likely go to the 60-degree column anyway. Okay? Any questions on that? All right. Okay, so what I want to do is we're going to go into our code book. Actually, we're fine with sharing that screen now. I switched. Okay, so let's go to our class right here. Let's go into our modules. And then let's look at our actual NEC code book right here. Where did it go? It's up here. Where is it? I lost it. There it is. All right, we're gonna open that up. All right, download it. Takes a minute to download. And we'll just open that up.
less to go on.
You guys need. Let's go check on these guys for a second, and we'll come back to the code book. What is it that you guys are doing right now?
Okay, so I did mine in like a little, I don't want to say a schematic, but I did a little drawing of what I think it should
Okay.
look like at the end of the day. So
That'll work. Okay.
So, and this could be completely wrong. I was thinking this here is going to the negative bus, the DC.
That is the negative bus, correct?
Right. As a label.
And it's labeled as DC.
Right. Okay.
Yep.
So I was trying to figure out where's this red one supposed to go?
That goes to the big breaker right here. So you need to put that bar in there,
Okay.
and you don't have that either. So there's two of them.
Let's see.
Okay, so we don't need all those big breakers. So you could take this 175. You got a 250,
250. Yep.
and you got a 250. So you don't need that big one in there. I would pull that one out.
It's heavier than I thought it would be.
Yep. So we got our 250 breakers. That's important. So one thing to help you guys is you got this book with pictures. And so, not that that is the system that we're doing, but it gives you variations in the way that this thing can be wired up. So what am I'm showing these guys this right here. So you can see their little map right here of what they're looking at. And let me bring it up. There we go. And you can pause that later if you want. That's kind of the idea of how you'd wire up this system, more or less. You got a generator, you got a wind turbine, you got batteries, you got controllers on there. Okay, so those controllers on the right side there would be, the gray one would be the generator start if you have a generator, and the one on the right of that would be a PV system. Okay, so that would be not PV, that would be your controller for your PV system. So the controller for the inverter all together. All right. So they've got a couple different ways of wiring this up that you can take a look at, which would be helpful. So mostly it has to do with how this part of it is getting put together right here, more than anything. Okay, but we got the real one over there. So when you look at this, this gives you an idea. We got a couple examples. So you can see right here, where would your positive one go? You can see your positive wire running right over here. See that?
Mhm.
And so we needed that, which is what you got there. And we're going to put that bar in there, just like you had over there. So if you go over there, you can see that. So I'm going to take them over there and let them see what you're talking about. I think you guys understand, but we can come over here. So what we got, their question is, they've got the DC bus right here, where everything's running into it there. And then down here, they did not have this bar installed yet. So now they're installing this bar. Now they're also installing this breaker. This breaker is a 250 amp DC breaker. It is a big breaker, and it's important because it is able to trip if we push more than 250 amps at once into this thing from our batteries. We see these big cables here, 4-aught. We see one right here. That is a 4-aught cable that's running to this bus bar. This bus bar right here is connected to this bottom screw. This bottom screw is just simply bolted to this bar. I don't want to touch this, but I know it's dead, but I don't want to touch it because the batteries are not dead. And I'll be honest, they're still alive over here. So safety-wise, we want to turn that off, right? So we got redundant isolation. Remember how I said we got breakers between this and that, and disconnects between this and that. That's what we want. So that's a 250 amp breaker. We can see our wires. We've got a negative cable coming to our batteries all the way down here on this side. We got our negative cable right there. okay? And then they are positive, negative, positive, negative, positive, negative, positive, negative. They are wired in series all the way down to here. Then we have our positive cable that comes up, goes through the breaker, back out the breaker, back into this channel down here, and through this pipe right here. Then it comes all the way over through this trough, and we can see the wires right there. So what we notice is there are these little caps up here protecting our wire. So we have more or less, we have a positive connection to our inverter for our battery, and we have a negative connection for our inverter on our battery. So the positive and negative connections, they now run from our inverter over to our bus bar, because the actual battery cables that run all the way through here, through our little trough, they go to the bars first. So the batteries come to this bar here or here. I have to figure out which cable it is. Looks to me like, yeah, this is the cable coming from the battery. So this cable goes to the battery, goes to this bus bar, and then we actually have this cable here that is on the top side. That is on the top side of this breaker. The top side of this breaker, then this big fat red cable, that runs all the way over here to our inverter. So just to be clear, we have our batteries over here. We know we've got a negative and a positive cable coming this way from the batteries. Runs through our trough, and then the negative cable goes to the negative DC bus right here. Then our positive cable goes from this to our positive DC bus right here. So what matters is when we shut this off, we're disconnecting our battery from this cable, which connects to our inverter. So these two cables are disconnected by this breaker. That's what those guys are putting in first. Okay, even though we don't have any batteries, they still need that bar up there. So now we're bringing all those cables in. We know we got those batteries. We know that's what we need to do. We know that's why that is there. So let's check on these guys. How you doing over here?
Pretty good.
So if I only want one of these, can I just do I have
Get
to
rid
go
of
through
this one. Get rid of the 175.
Well, what about this thing right here? 'Cause
You
this
need
thing
the
is-
bar. Come over here. The bar is right there. You just don't need the breaker attached to it.
Oh, I see. Okay.
Okay, make
Gotcha.
sense? That bar allows us to bring in multiple things to this one breaker. And then we don't have to have like 5 250 volt breakers.
Mhm.
We have a bus bar.
Then a change I did make, I attached this onto here. Is that the right
So,
area, or is...
No, not necessarily. Come over here. Well, let's verify. So, you're okay. I didn't say you're wrong. I
Because
said not
I
necessarily.
just looked at how Patrick's already set up, so I was like, well,
Well, that's all right. That's why we have this.
yeah.
Let's just go over this. I went over this with them. We know you don't have any batteries yet.
Mhm.
So you don't have a battery cable coming over. So one of those cables coming over in this trough through this pipe is a positive or a negative cable coming from these batteries that you do not have.
Yeah.
What you do have is a cable coming from your inverter. So you have a positive and a negative.
Yeah. So I got the negative one over there.
You got the negative one. It needs to go to this bus.
Yeah.
And that is what you got. You are perfectly fine.
Doesn't matter which slot.
Nope. Because this
Okay.
is all a
It's all the
piece of
same.
metal. It's all the same.
Gotcha.
Now, eventually, you're going to be bringing a battery cable from whatever battery set we want into this. But this is bimodal. We don't have to have batteries to run these inverters.
Okay.
We have some, but you're just setting yourself up. So if we want to bring a battery in, all we literally have to do is come in and land the negative there and then the positive on this right here
Gotcha.
when we get ready to do it. Okay?
Do you want us making marks like they do right here?
Those are torque marks?
Yeah.
Not yet.
Okay.
Not until we've done any commissioning.
Gotcha.
So that's last. And we got to know our torque values.
Mm.
So what is the value? We don't know. It's probably 20 pounds is fine. But I wouldn't worry about that because we pull them on and off. But that's why they're there. So no, but technically in a full system, if you're building it for a customer, yeah, you would have to do your torque value marks. Okay? Righty tighty, lefty loosey. You're going to the spin it with your hand. Like how would you tight? So that would be tight, that would be loose. So you want to turn it this way.
Gotcha.
There you go.
Okay, I see.
So that's how you can correct yourself real quick. Try that. Oh, you do it.
Man, I remember putting this.
All right, put it on the ground.
Like whoever put this made it.
When you do with this stuff, put it on the ground.
Must've
Put
just-
your wrench on there and step on it. Put your wrench right there. Yep.
Oh, I can use on that one too.
Now stand on it. Stand on your wrench.
No, on the wrench.
Yeah, stand on it. Don't jump on it.
Sorry.
Push on it. Yeah. I mean, you can do it that way. When you're in the field, you don't always have stuff. So now just put your weight on it. There you go. It busts free, right?
Yeah.
So sometimes just putting it on the ground, put your foot on the wrench, put your weight on it. You're ready to go. You don't got to go get another tool. Okay? Good job. So they're working on that. Let's get back into what we're looking at. So we know where they're at. They're hooking up batteries right now. What are we doing? Well, we were looking at our NEC code book. So we're going to pull that up. I'm going to share my screen. I'm going to take a look at this code book. So we know that this code book is something that we need to find the right table. So it's like table 3, 10, 15. So we are all the way down here looking at chapter 3, which is where we want to be. All right, so we're going to go to like page 154. Okay, now we're going to want to run through this and find that table that we're looking for. So this is 300. We need to find 310, 15B, not this one. Not that one. That's one that we use, though. That's our ambient temperature one. There's our number of conductors and adjustment factors, more than 3 carrying conductors per conduit fill. There we have our roof adder right there. We've used those already. And here we are in the chart that we want to look at. So this chart is allowable ampacities for insulated conductors rated up to and including 2000 volts. Okay, so this is for conductors in a raceway. So we're in a raceway because we're running pipe to move our conductors around. So we were talking earlier about what we need to do. Well, we know that we're running up to 60 amps. So we can go down here and look, where is 60 amps? So you can run up to 55 amps on number 6, okay? If it is TWUF. Well, I can tell you the insulation that I always use, if I can, is THWN-2, which we've talked about that in a previous class. That means it is thermoplastic. It is high temp. In other words, it's a combination of THHW. Okay, so it is able to be done in wet locations or submerged water, not just damp. But because it has this 2, it also is able to be rated at a high temperature. Okay, if we look over here, we see we got TAHW. That cable is only rated for 75. Or THWN, that cable is only rated for 75 terminations. Or that means that cable can get up to 167 degrees Fahrenheit, which is much hotter than the water that you take a shower in. The water that you take a shower in is about 120, when you have it turned all the way up. It can be pretty hot. But that shows you it doesn't take a whole lot more. But 194, yeah, that'll cook you. We know that's bad. That's not something you want to stand out in the sun, right? So that's hot. It's definitely hot. So if we felt that wire, it would burn our fingers, okay? So we know that it can get that hot to where if we touch the wire, it would burn our fingers, even though the insulation was there. But we're trying to use THWN-2 wire because it's versatile, right? It's a high temperature rated wire. And what does that mean? If we use number 6 THWN2 wire, that means it can handle 75 amps until we derate it, of course. We also need to understand that our terminations are, according to that charge controller, can handle 90 degrees. Okay, so that means that we're under this column here, but let's say we're not sure on terminations. That means we're limited to 55 amps on a number 6. But that's only if we're using this type of wire. We're not using TW or UF wire. We're using THWN2, which we know that wire can handle 75 amps. So because we put a limit of 60 amps on our system, we don't really worry about the fact that we're running only 60 amps to this THWN-2 number 6, because the breaker is going to stop it at 60, but we know right here that that wire is made to handle 75. So our wire is probably plenty big. So if you said, well, it's not big enough, let's go to number 4. Well, that means, yeah, under the 60-degree column, you can handle 70, but number 4 is rated for 95. It's quite a bit bigger and quite more expensive. And it's not something that should be an issue here. So in this case, we installed number 6 because we know the wire that we chose can handle 75 amps, even though we're going to keep it under the 60-degree column for sizing. Okay? All right, I know it's a little confusing, all right? Or 75, but we're okay. We're definitely okay because the wire is what we're worried about. We're not going to be able to bring more than 60 amps into this system that we're building because the breaker will trip. So our charge controllers, all of our equipment is protected by that overcurrent protection device, that circuit breaker. We also know that even though our wire is going to be on for more than 3 hours at a time, that we still have this play of 75 in there. Okay, now I can tell you that this wire works just fine. This thing has been here for almost 10 years, literally 10 years running on 6-gauge wire, and it's not a problem. It doesn't get hot. It's plenty big. A lot of times we fail to realize that our solar systems aren't running at 60 amps full blast all the time for more than 3 hours. So when we're talking about, does it need to have 3 or more hours of protection? Yeah, you put the 1.25 in, but that's if it's at 75 amps or 60 amps for 3 hours straight. These can do that, but as we've seen, they're going up and down as the day goes by. And so, yeah, they'll be lucky to have 60 amps on them for 3 hours straight. So the wire's never even getting that hot. Okay, but you got to think about that. But that is where we get the size of the wire for our system. And that is the logic behind it. Okay, and I know we have those little charts that we were working on because there's more to it than that. We've got our surge capacity, we've got our ambient temperature correction factors. We have all that stuff that we have to take into consideration, okay, as we do this. And anyway, so that system, that's how you find that in the code book. All right, so let's go back to our book here. So what we're learning is how to size our wire. So we chose number 6 is what I'm pointing out. And I told you why we chose number 6. And now, because we know the size of our power cables for our system, number 6, we know it can handle 60 amps, which we have 60 amp breakers all over the place, limiting our ability. That thing is pushing 5,000 watts. I really wish the other one was on. It is humming. We are killing it. We're making 10K right now. Let's take a look at our opacity here. 308. That tree must be blocking it or something. That does not make sense to me. I might need a battery in it. Normally it goes right hand in hand. So when the sun goes down, that meter goes down. When the sun is cranking power, my inverters are cranking power, and also my solar insulation is at, closer to 1,000 watts per square meter, not like 300. So that could be a sensor issue, but that's what we should see. It's also because we got a very cloudy day, and so what's happening on this side of the yard is not necessarily what's happening on that side of the yard. So we can go out there with a meter in our hand and test that physically. But right now, we've taken the time to look through what it is that we need to size our cable number 6. And because we're looking at grounding, we need to size the ground wire. Well, what do we say? We need a number 6. So number 6 is smaller than number 2. Okay, so number 6 is smaller. Number 2 is bigger. Just make sure you understand that. All right, and then where that leaves us is if we're using copper wire, which we were, that is number 6, which is 2 or smaller. That tells us that we need a copper electrode that is that number 8. So we drive that in the ground, and now we know what our size of our green wire is supposed to be. It's really that easy in most cases. You can make this way too complicated. And what I say is like, okay, you're getting all weird with rocky soil and stuff. I'm just going to go with a number 8. I'm going to go with a number 4. I'm going to change the size of my wire, and it throws all those concerns right out the window usually. Like, oh, that's big enough. Well, that's fine. It only cost me 50 more bucks, and I don't have to deal with this headache. That's another way you can solve it, Or you can get in there and do the code calculations till you turn your face blue and hope that they're right on the money because you're trying to make your wire the biggest it has to be to save yourself 50 bucks. You're asking for it. It's better to just oversize these things that are really tight on the numbers. Like number 6 is tight. I'll tell you that. I would have liked number 4 better, but it raised the cost a little bit more because we're going 200 feet with parallel conductors. It just raised the cost. So we had to make an executive decision and go, it'll be fine. It'll be fine. And it is. It's fine. But you got to know it'll be fine. Okay? So in this case, you want to make sure that you size the system properly and you don't know what it is, oversize. Anything that is metal, we're going to want to bond to that green wire when we're looking at grounding. Okay? Then they have these things called ground grids, which are literally things that encircle around the property or different grounding electrodes all over the property. You don't need all that. What we would call a ground grid is you have a grounding electrode right here at our main panel. So if I were to go outside on the other side of this wall, in most people's homes, on the other side of the wall, you would see your meter. Like when I say other side of the wall, I say other side of this wall right here. You'd see like your electrical meter, and you would look down below and you'd see the grounding electrode on the ground. We can't see it because it's not that side of the wall, but we would see it, and that would be one side of the ground grid. Then we'd actually have to go outside and actually see that connection out there. I would take my computer with me out there, but I don't know if I'll lose my connection. I'm not ready for that. Maybe with our little GoPro, I think we can do that. So I'll be able to walk around. Now, what we also are able to notice is that we have determined that we know what our ground grid needs to be. Our electrode must be 8 feet. We already determined that. We know what it needs to be. We said 5/8 number 8. We already did all that. Now we're beating it into the ground. And now we've got some of these other things that say each plate electrode must have at least 2 square feet of surface exposed to the soil. Electrodes of iron or steel plates must be at least 1/4 inch in thickness. Just beat it in the ground. It's going to be sticking up about that much. You don't want the thing sticking 2 feet out of the ground. That's not what they're saying. If you are, you're going to trip over it. No, it's going down into the ground. More in the ground is better. Okay? Because you're trying to get as many of those electrons into the earth if you have a fault. So the deeper we go into the earth, the better. So in this case, let's move on. All right. So I'll tell you, a lot of this stuff right here is just a lot of extra code stuff that isn't really that applicable. Now, you do have some issues of if you're going to connect to a pipe, don't do it. Don't do it. Just don't do it. That's all I'm going to say. I don't teach any other way. So if you take your ground wire and you don't attach it to a ground electrode that you put out in the ground yourself, you're asking for it. Because what people will do is say, well, I've got this pipe that goes to my well, and it's deep in the ground. Can't I use that for a ground electrode? Yeah, you can. But if you ever take that pipe off, you've completely ungrounded your system. And I've seen it where someone will, I actually on the side of this wall, I have a pit, and I could show you, but what would you see? You would see a pipe coming from water well, and you'd see a bunch of ground wires attached to it. But as soon as someone cuts that pipe out who doesn't know what they're doing, you no longer have a safe system. You could literally walk out there and put your hand on metal and get electrocuted because you don't have a path for those electrodes to those electrons. If they get free from the solar panel or the wire insulation, they get free because you got a nick in the wire or you got a fault where the wire is now touching metal when it shouldn't have done, but it's doing it because you didn't tighten the screw down and it fell. Now it's touching the side of the metal, and you go out there and put your hand on it, and you don't have a properly grounded system, you could get electrocuted. So overground things. Don't take the cheap shot. Don't do the pipe. Yeah, the code allows you also to take wires and twist them together, a big bit like these number 6, and wrap them with tape. Nothing else. No screws, no terminations. Tape is good enough because we've done that for 1,000 years. It is not good enough. Don't do it. Just because what the minimum is in the code is not the best installation. I say that over and over. So most of this stuff right here in this chapter is the excuses that you can make to save money. And it's just a bad installation and unprofessional. So I know some people would disagree with me. They think it's okay to connect to pipes. I've been doing this in industry for 15 years. Anybody I ever met who knows what they're doing will not do that, because too often we've seen people disconnect your ground from metal pipe because they remove the pipe. And you say, you can't do that. Like, well, you can't bond to my pipe. That's my pipe. So make your own ground. Point made. So everything needs to be bonded together. Bonded means all these things need to stay connected. So if we pull that pipe out of the ground because we're removing the well and we don't put a new ground electrode in, we're no longer bonded. So we need to make sure everything that is metal, that is part of the system, is connected to a green wire, one way or another. And we have several cases of that throughout the system. Okay. So then you start to see some of these weird things where they're trying to cut corners, where they can't go 8 feet because there's rocks down here. And then you've got to go to the right here. Well, I can tell you rock doesn't really have water. Rock is not a good ground material. Ground material needs to be dirt. Dirt with water and moisture in it. Sand, that is not dirt. That is sand. It can be moist, but it is not a good ground. Moisture is what attracts the electrons down into the earth. So when we have rocky soil, one of the things you can do is come in at an angle. You're still getting enough of the dirt around it, you know, but it's still 2.5 feet underground is not as good as 8 feet down. I would move. I'd say, I'm hitting rock, I'm moving. And I keep trying until I got this thing driven down as deep as I could. Okay. Now in this case, they're showing this underground. That's not what you do usually. You can, and that's fine. All right. But that's typically not what you're going to do because you don't connect and disconnect things underground like this. So this would be up out of the earth just a little bit with this little clamp on there that we looked at. Now you can also put multiple grounds in. Say like, I don't like this. So if you want, you could just keep putting in grounds all day long. It ain't going to change anything. But what you need to recognize, it is common for 2 ground rods to be installed when the resistance to earth through 1 rod is not 25 ohms or less. So that's all you're really trying to do, is you're trying to measure between the rod and the system, or between the rod and the earth. Okay, so if you don't have, you're like, how do you measure between the earth? Well, you can take a screwdriver and stick it in the ground and touch it with your meter, and then touch this. Because whether or not you realize it, the earth is an electrical conductor. So you can conduct electricity from this rod to this rod through the dirt. We can put a light bulb here and a light bulb here and run a power to this. And because these are connected close enough, they literally, without this connection here, they literally could power each other. That's how Tesla coils work. So when we're in the earth, we got to recognize this is a conductor. The earth is a ground wire. The earth is a conductor. Okay? It won't electrocute you if you're standing on it because, well, it's not going to go through you when it can go through the earth. It'll go just right around you. It's not going to go up through you and back down. Why would it do that? That's harder. It's just not. It's going to go through the earth. So what we end up with is the idea that we need to make sure, in the most simple sense, that our ground rod is measuring 24 ohms or less. If it's not measuring 24 ohms or less, then we have to do something different. Generally add another ground rod in a different place and connect them together, or move it somewhere else, because you're probably in rocky or clay-like, sand-like material instead of good dirt. Any questions on this? Okay. So what you find is there's a lot of exceptions that go through here that I don't expect you to remember at all. And what you want to do is just quickly read through this and get an idea. But remember what I said. When it comes to actual installation and stuff, that's how you do it. You know, and there's always somebody there to nitpick and say, well, code says this or that. And I say, you know what, though? I'm using number 4 wire. So what are you saying now? Oh, well, that's different. Yeah, I know. Okay? I don't want to deal with all those little code things because they create issues. So we want to make sure that we have a solid ground, our own ground, at 24 ohms or less. And if we need to add more than 1 grounding electrode to do that because we're in rocky soil, then that's what we're going to do, because those electrodes only cost $10, don't they? So stick them in the ground and put several of them. But you shouldn't have to do that around here. We have pretty good soil. We have really good soil, right? This is ag country. So we're just going to run those things in the ground and never even worry about it. I'll be honest. You're not going to worry about it. They have like no ohms on them at all. 0. You know, you're not going to see 25. You're going to see like 2 most of the time, if that. Okay. Let's move on to our next section. So this is what I was talking about in clarity when we're worried about bonding to this pipe. So they've got their electrical panel, then they're running their bonded ground wires out of this panel down over here and bonding it to this pipe. Or if we remove this water pipe, then you've lost your ground. See my point? Don't do it. Go buy your own ground rod and run it down there. This is lazy. I don't like it. I don't like it at all. And a lot of people argue with me. I don't care. When I'm your boss, you're running it this way, and that's what it's going to be. And when we run neutrals, you're running your own neutrals. You're not sharing neutrals. I don't share neutrals. You run your own white wire every time because it causes problems. So we run for every circuit that you run. If you have a white wire on an AC circuit, it needs to have its own white wire. We don't run one white wire for 10 black wires. You'll see that. You'll see that in the field, and they'll try to explain it away. How does that work when all these are pulling 20 amps and you got one wire that can't handle even 20 on its own? There's a lot of things that you just don't do because if you don't think about the situation that you're putting yourself in, you'll run into problems when you're trying to get your system to act right. You'll overheat, you'll trip breakers, and it's because you cut corners. And the worst thing is you'll start a fire in a home and people will die because you didn't follow code properly, or you took the minimum and you didn't protect persons and property. That's what your goal is as a person who works with electricity. I'm a qualified individual. That's why I have my rules. When you talk to me about running this, I'm going to say, why? Why are you doing that? Oh, because we can't. Oh, well, you're a cheap ass is what I'll say. And I don't like it. And we're not doing it that way because I'm not protecting persons and property. I'm worried about that. And you should be too, because I want people to feel like they have a good system where their children can't be killed because of a fire in their house because some idiot tried to save $100. Understand? All right. Well, I see that a lot. And you guys are professionals, so you need to be better than that. So keep in mind that the grounding of the system right here, this is our equipment grounding electrode. So it runs from here to here to here. This green wire is connected throughout this whole system and is going to be bonded to this system. And that means in case you touch anything, you won't get hurt. So lightning protection and surge arresters, we're getting right here to the end. Lightning protection and surge arresters are important. I think I've cut corners on that, and I paid for it. Don't do it. I don't have any of that on any of our systems here, and I need to do it. Because if we get a surge from the grid or the lightning, then we just blown basically our stuff. And so we don't want to do that. All right? Okay, so disconnect, we've already talked about that. We've already talked about marking requirements. Okay, this is something you need to know. This is a lot of stuff I know, but that's why we're still in chapter 9. Section 690.53 requires permanent label for DC PV source circuits to be installed at the PV disconnect. We know that already. All right, so the rated power point voltage, as we know, is VMP. We know we do calculations with the maximum voltage by multiplying the VOC by the correction factor based on ambient temperature. So they're just reiterating stuff that we've already learned here at this point. Let's see here. 4, 5, 6, 7, 8, 9, 10. Yeah, we're going to go through this stuff pretty quick and make sure this is all clear. Surge arresters, we know what that is. Okay, this is just giving you some graphics on some of the stuff that we've already talked about, making sure that you have your labels on your equipment. We have labels, see, right there, big red label. They're all over the place. You're gonna see them over there on those systems too. Okay, we don't have labels on our pipes, which we should, but this is a lab. So labs don't fall under the same jurisdiction as code, but we do build this stuff to code. But we pull the pipes down and up, and we know they're all PV circuits. So anyway, all right. A funny story was I had an inspector come here once, and I invited him because I wanted to know what was going on. And I used to work with him. He used to be my journeyman. And then I realized he didn't know what he was doing. Then he started flipping out, trying to get me on all these things that were code violations. And I said, you can get out of here now because this is not your jurisdiction, buddy. And then out the door he went. It's not. Okay, campus is like its own city. So we have our own jurisdictions here. And it's also because it's a lab. So it's different. And so I find that even your inspectors don't know some of the codes on this because it's so new and they don't really know what they're looking at. So it's important for you as an installer in this area and at the very beginning of all this to try to understand this as much as you can, because you know you're going to have to do some of these things that if they get in there digging in the code book because they don't know what you're supposed to be doing and they start finding, well, you're supposed to label these. All right, I'll label them. Yeah, I need to label them. You know you need to label them, so make sure you label them. Some of this other stuff in here, it may not be quite as obvious of what you need to do. But part of practicing this in class and just seeing what it is that you need to do, then that'll get you there. Okay. So this is just more labels, telling you the different types of labels that you really need to do. So I don't have a problem with any kind of label. I like labels. So make sure you label your stuff with red stickers. You can buy a printer or you can order them online and then you got them, okay? Order them online is usually what you want to do because they mostly say the same thing. Or they'll have a little white space where you can write in like 60 amps or some number in there, and that'll do the trick too. Okay. Yeah, see, a lot of this stuff starts to make you feel sick because you're looking at all this information. But no, when you look back at what we're looking at, again, we're just looking at the fact that we got a disconnect in between each device. And then we have a ground cable grounding everything all the way through. That's all they're really showing you here, even though they're overcomplicating it. Now, they've also said inverters dedicated to solar systems, they need to be down here on the bottom panel. No, they don't. No, they don't. I don't care what they say. I've got a panel packed full of them. Where am I going to put them? I can't put them all at the bottom. So that's not true. So you can have these anywhere you want. Ideally, they want you to put them at the bottom because they're just kind of any big loads. That's what you want to do. If you've got a 30 amp stove or a 40 amp circuit, a car charger, you don't have very many of them. You got those 30, 40 amp breakers that are 240. You put them at the bottom of the panel if you can. But it doesn't matter that much, okay? Because you're going to have to put them in this panel. And then normal breakers are fine. A lot of times they'll say you have to buy these expensive DC breakers. Well, there is a little bit of perception that DC breakers, when they're turned on and off, create a little bit of a spark. It's kind of like a green spark if you ever see it. And if you do that, then it might wear the breaker out. I don't turn them on and off that much. I turn my light switch on off every day, but you don't do it that much. It doesn't matter. These breakers have been here 10 years. They're fine. They work just fine. So a lot of this stuff you learn with experience. And then you can type in the code and go, hey, these are fine. I don't know what you're talking about. And then they'll just make an exception in the code if you can prove your point. That's what the code is. It's just made up of people who know from experience when we need to think about what we're doing here. Okay. So when we start to get into this stuff, guys, this is where we need to reflect back more into our INDT 125 class, because it's not just a paragraph. You know, we're looking at more and more stuff in that class on how would we size panels and things. Okay. But when they're talking about this, they're throwing in the concepts of having a 20% safety factor. So, in other words, if you want that 20 or 25% safety factor in there, you've got to reduce this 200 amp breaker. It'd be 150 amp, okay, or connected to a load center would be 90 amps. So you have 120 times 1.25 minus 150 equals 90 amps. Well, I'm not even sure what all they're trying to drive at there, but the truth is that's a little bit too far on what you need to worry about. So really, this stuff, you can read it, you can take it to heart, you can put all your breakers at the bottom of the panel, and you realize it doesn't really matter that much. Okay. But what we do want to do is get back into this idea of these safety factor calculations, which we will come back to. Okay. All right. When we look at our breakers, just remember the top of the breaker is where the power comes in. The bottom side is what comes out. That's line and load. But when we're talking about solar, it's like, well, which is which? My generation's coming from outside, and that's my line. Okay, and my load is your house. That's right. Okay, but you get another electrician in here, and they just can't think right because they're like, wait a minute. The load is not the house. The load is the line. The solar system is the load. No, the solar system is the generation point. That's the line. So, yeah, doesn't really matter. Generally, I just try to bring every power, all my power sources, I always try to bring on the top side of the breaker. That's the line side. Okay, anything that's a power source, put it on the top. Anything that it would power, put on the bottom. Line load. And then that should be the way that you do everything when you do electrical work. Okay, and then people don't get confused when they're looking at it like, why does that look backwards? Because it is backwards. All right. And then we have our final. Okay, so that's chapter 9. So I was hoping that on the last part of this that you got a better idea of what you really need to do and how you need to wire this up and what is most important. There is a lot of code in here, but it's overdone, especially on grounding, way overdone. Okay, all we're needing to do is make sure we understand how to size our actual conductor wire, our equipment grounding conductor, the green one, and it's going to match or be bigger than our main power conductors, like our number 6, which we talked about. And then follow this chart on how big of an electrode you need. So if we're doing 1/0 wire, we're going to have to get a bigger grounding electrode. And if we're not buying copper, we're buying copper clad aluminum, we're going to have to get a different size too. Okay, let's see here. Okay, so I think that's all I wanted to do today is just wrap up that last chapter. I also know that a lot of you guys still need to do your midterm. Okay, so I'm not going to add anything new. We've wrapped up chapter 10. Does anybody have chapter 9? Does anybody have any questions for me? I'm going to have to start asking questions, aren't I? If you don't have questions, then I'm going to be done here, and I'm going to let you go. And I'm going to come back over to these guys. If you want to stick around, last time I said that everybody just disappeared. So then I just shut the class down. So if you're going to stick around, that's fine. If you're going to disappear, that's fine too. I just don't want to leave my computer on if you're not going to be there. So I'm going to go over here and check on them. You guys need to stick around and watch what we're doing. If not, you're dismissed for the day. Just work on your midterm exam and then try to get all your homework done. Your next lesson would be this one here. If you've already got all that done, everything done, then you're going to have a good weekend. And then you'll start to see week 6 pop in there probably today or tomorrow. I'll try. You know how it goes. I only got 2 hours left. So anyway, I'll see what I can do this last 2 hours. I'll try to get that. I got to get ready for next week anyway. So we'll be popping that in there with your lesson plan. And then we'll touch base on Monday. I will be here on Monday at 7:30 in the morning, 8 o'clock. And then I'll be down at the other lab first thing and see if they give me my computer back. They took my computer with all the discs. So I don't know if I'll be able to do anything on the trainer. But if I get that back, we'll be able to maybe do some. It was the goal to try to actually do some troubleshooting on that trainer. But I'll figure something out. And then you'll be able to show up if you want to on Monday or Wednesday until the end of the class, just like this. And that's what I plan on doing. All right. Does anybody have any questions for me?
So if we show up for 8:30 class, where do you want
You
us to
talking,
meet you at?
Josh?
Yeah.
'Cause I literally can't hear anybody.
Can you not hear me?
That's terrible. Well, I'm assuming you guys could hear me just fine. But if you're not talking, I can't hear anybody. I thought everyone was able to hear me. I'm pretty sure you can. I'm just going to let you go. And I don't see anything on the chat, so I'm assuming we're all good. And I will let you guys go, and I'll get back to these guys. So have a good day, and let me know if you have any questions or anything. Bye-bye. All right, guys.
All right, I got some ideas here.
Okay.
So, we're looking at the schematics here, and it's got another box right beside of this switch circuit breaker that comes from this charge controller, and I was wondering if that looked correct. If I think it is, 'cause
You see that over there?
they got the
So
same.
there's multiple ways we can do this, right?
Okay.
So over here, you see that box?
Is that the two?
I'm not sure what you mean.
This little box right here, coming from the charge controller, there's one,
What do you call a box?
I'm sorry, this disconnect,
Okay,
DC disconnect.
so those are these disconnects here.
Right,
We
okay,
need those.
right, okay,
Okay, I don't think we have those. We're gonna put those on our list to order today.
okay,
Okay,
so that was.
that's a
that.
question. Okay,
And that would take care of the two wires, and then for those two wires, let me figure. Just a second, I got some more.
And then my question is,
Oh, yeah, and then would this ground wire go into the ground bus?
Yes.
Okay,
yes.
so then
So all green wires, it doesn't matter. So we got two different bus down there. Look at the bottom.
Yep,
It
there's
says
another
ground bus.
and
The
then
other one
ground
says,
bus.
but doesn't say DC or AC, does
It
it?
just says ground bus.
That's because ground is the dirt outside. This is kind of like what we were talking about earlier today. So those wires connect to the grounding electrode that goes to something outside. Doesn't matter if it's DC or AC.
okay,
So,
so yeah, because
Whichever one's closer is what it is.
All right,
yeah, the diagram on there showed this green cord going up to here, but this one's already installed. Does that matter?
Nope, because this is a ground bar. And what you need to recognize that it's a ground bar because you see this is touching the metal. This is touching the metal. This looks like it's connected to this. It is not. See that space? You say, this bar here looks like it's connected to this, but it's not.
The plastic right there.
This is plastic and this is plastic. So this negative is isolated completely from the metal and the ground bar. Does that make sense?
Yeah.
So yeah, you can put any green wire on this one or this one. And this is the neutral, not the neutral. This is the negative. This is the neutral. There is an AC neutral up here. But we notice again, there's these plastic
Yeah, right.
blades, if you will. Lifting that stuff off of that.
So then this little red guy needs to go in behind here, but I need to take this piece off there. So or do I need to
Yes,
keep this
no.
piece?
No, all you need to do is, you're gonna watch these things getting twisted up on you. So I like to put everything together. So this is crossing. It's not necessarily something you did, but yeah.
I totally did that, because I installed that on there, that's wrong, so I probably should have.
What do we got here? So these are what you're calling your AC load. Let's make sure that's right. So line 1, line 2. Oh, I'm not sure what we got. So this is our AC load, and that is our grid. Okay. Not necessarily against that. Grid is different than AC load.
Got it, I didn't put this for you.
You didn't put these?
No.
Oh, I thought you said you did.
No.
Okay, so all I'm saying here, these are going to the sub panel that we don't have. So that would be, let me just put something over here. So over here, we don't have a generator, right? So that would be if we had a generator, but we don't. So we'd run those wires there. And then that would require a special controller too, that we don't have.
Hmm.
And I'm gonna get one, I kinda like the idea of one. Then we have the grid AC right here, grid AC, one, and oh, that's a good idea. I should get us a big ass Generac generator, because I've been wanting to train us on that.
What's a Generac?
Generac is the brand of
Oh,
the
okay.
generator.
All right.
That's the one that everybody goes to. That's the best one.
Rolls
Right?
Royce
The
generator.
Rolls Royce of generators. And so a lot of the companies that you guys work for, I've heard them ask, like, can we get them generator certified? I'm like, maybe. What do you want me to do? Well, I don't know. I'm like, well, you got to tell me. Well, we want to go through this certification process, and like for one or two people, just a couple. So you want me to create a whole program for two people? Can't do that. Sorry. So, but they want. So I'm like, okay, maybe we'll start to dabble in that, and then we'll be able to cross that off our list. So we don't have the generator, but we do have the grid. So we know this is going to be coming from the grid. So that would be the wires that we said were hanging at the beginning from the panel. They're going to have to come in to the grid. And we recognize, well, what is the grid? That is this breaker here. So that means we know that the line side or the power is coming in here and there. Okay, that's the grid. And the bottom side runs all the way to here.
Yeah.
Then you have the wires that we're talking about over there. You have these being the AC load center. So where do they go? They run through here and they run into this mess also. So they're coming in, we have to chase them down. But they're coming in and they're, so we can see our neutral wire right here is there, right? Okay, and then we can see that we've got, the best way to do this is pull your wire. As you're feeling your way through this mess. There we go. That's not it. It just disappears. There it is. No.
This one tugged when you pulled.
Yeah, it's weird. This one? This is the one we want. It's way back here. Here it is. There it is. Okay. So it's running up on the back side here. Right there it is. Yep, and it's running to the top over here, which is what you have, isn't it? I think so. One, two,
Possibly, yeah, I
three.
think so.
Let's go check. So both of those should go there. I believe that's what you have. So you got 1, 2, 3. Running to the top. Black, red. Awesome. Yep. So what we want to do is we don't want to twist these. So when we're thinking about them, they're going to all going to be bundled in the tie wrap, right?
Yeah.
So we got this dude right here pulling us out of our bundle. So that means I would pull this out, bring it back to the front, leave that on the face. You see right there, you crossed it there too.
Yeah.
You're gonna pull, so actually you did do the crossing because you put this wire in. So you want to unbolt that and put all of your big wires, including this one, on the back. And you want to pull these to the front so we can work with them. So just, that'll come back and get you. So your original question is, do I need to put this here? Yes. But before we do that, clean this up a little bit. And then you can go from there.
And then will I be actually placing these cords anywhere today? Somewhere?
Yeah, we can.
Like where
They're going to go on this breaker here. So these are power cables, so let's keep them out of our face first. I'm in a hurry to hook them up. Once we hook them up, then you have the potential to be electrocuted in this box.
Gotcha.
So I'd rather be on the floor. Okay? And they're off over there anyway. Once we put them in, we're gonna start turning things on and off, and then we're gonna mess up and possibly forget that we left it on. Right?
I've got kind of the same thing on this schematic here with the AC breakers. I see we've got 3 of them all connected with
So do we have any more 60 amp breakers for you?
I've been looking around the table, but haven't found any. I don't know where to look in the tool.
Okay. I don't think you do, but I know we got these 2 here. If you want, take these 4 off. Let's take a look at them and see if they're even connected to anything. But there's nothing to them. We're gonna rip them out and give them to you. I think they are going, oh, I already know. But let's look at them anyway, because that's all I got, I think.
Okay.
So we could pull these off and ship them over there to you.
All right.
I think we're bypassing these anyway.
Okay.
So it should be off, it's off. And they go to this inverter 3, which I'm gonna turn off as well. And then over here. That's inverter 5, isn't it? Where's that inverter 3? Inverter 3. Where's inverter 3 go? I know where it goes. All right. Patrick?
Yep.
Inverter 3 has power coming into it.
Okay.
I'll show you a couple things. This should be less likely to be hot, but I turned it off. So that's the grid coming in over there to inverter 3. And then it has a sub panel, which is also off. So none of these loads will work. And they shouldn't matter because we're bypassing that thing. So if I turn this on, they're all going to work as long as the grid's on.
Okay.
So what we're doing over there, I think, and what we should see, is we have the grid running all the way over to the panel, and then we're just going straight through and feeding this.
Okay.
We're not doing anything but that.
Got it.
So if we rip out those breakers, I think we can take them. And honestly, I think we can take them. They're already gone, aren't they? So that's what I'm gonna do, sitting here with you guys while you find wire this up. I'm gonna get on that website and look for all these things. All right, and order them.
Yeah, right here.
Yep. Let's just first pull this off. Let's take a look.
I'll do.
All right.
It's good, but oh my god. Did you
Back
pinch
your
yourself?
hand.
Yeah, when I was undoing this, I was holding it like this and went right into my
I
thumb.
won't do that again, will you?
And my thumb's already purple.
I hate that.
After what I did is when I was untightening this, I had my thumb right here, right? Oh yeah. So I went swoosh and smashed the wrench right in my thumb. I wanted to yell out so many more words out there. It hurts so bad that moment. Okay. A lot going on. You know the like numb feeling you have when you smash your like thumb or something on something? Sorry, what? You know what I'm saying? You smash your finger or something like that. You know, like that numbish feeling it has like that because. Yeah, I see what you mean. Like it's not numb, but you know it's just, like the feeling is kind of not as much there. Yeah, that's basically the old best buy I got. But yeah, let's see what you mean.
All right. I'm going to move this over here. Jamaica, are you there? Do you have any questions for me, or do you have anything you want to look at? I just want to make sure you're there. I don't know if anybody can even hear me.
I think they can hear you. I don't know. I feel like some of them just aren't. I think they're just mostly relying on someone else to speak up first. So they don't have to.
Well, there's only one person left.
I think, yeah, there's only one person.
Well,
but
but
earlier,
in general, yeah. I'm not even sure if I'm on half the time.
I don't know.
Yeah.
You're, if
There we
I
go.
think you're